I'm excited to give you a talk about the brief history of quantum computing. Before I start the talk, I want to mention the famous saying by Richard Feynman that if you understand quantum mechanics, you don't understand quantum mechanics. So if you cannot follow my talk today, it's not because of my presentation, it's because of Richard Feynman. Let's start with something we can understand. Let's say I throw the rock on the lake, then the ripple will spread out on the lake. And I set up the wall with the two holes, so the most of the wave will encounter the wall and get blocked by the wall, but some of the wave will go through by these two holes. And this wave will meet each other and make some interference, make some pattern, which is called interference pattern. You can notice that in the water wave, you can see the peak is amplified. We call it constructive interference. And you can also see that peak and dip meet each other and cancel out. We call it destructive interference pattern. We can find this phenomena every day in our life, such as water wave, sound wave, and actually that's how you cancel the noise from the outside on your headphone. In 1801, Thomas Young discovered that light is also a wave, like a water wave and sound wave, that can generate the interference pattern. He designed the experiment that sending the light to this double slit and saw the interference pattern, constructive and destructive interference pattern. And about 100 years, there's no problem treating the light as a wave until 19th century. Beginning of the 20th century, things start to change. People were having difficult time to explain one simple phenomena. They shine the light to the material and electrons are coming out. And it's not dependent on the intensity of the light, it only depends on the frequency of the light. So it does not matter how bright light you shine into the material, only the frequency will decide the electron will coming out or not. And Einstein showed that light must be made by some kind of fundamental particle called photon, and he found the relationship that the energy of the photon will be proportional to the frequency of the light. So which means that when we have a fast oscillation, we have more energy, more momentum, and when we have a slow oscillation, we have less momentum. So then higher momentum, higher frequency can hit the material, extract the electron out, but lower momentum, lower frequency cannot extract the electron out from the material. And he concluded the contradictory result that light is a particle and get a Nobel Prize and become a star in physics. Now he showed the light is a particle, and what's going to happen if you repeat the double slit experiment again? So, light being a particle is not a problem to explain the double slit experiment. We know that water wave is a collection of the wave, a collection of the water molecule oscillating, and sound wave is a collection of the air molecule oscillating. So the light wave is also a collection of the many photons. Same logic, we can see the interference pattern. No problem. However, when you send one photon at a time, like let's say one particle at a time, we should not expect to see the interference pattern, because interference pattern only happens when the two waves overlap each other. So unless we send the two photons together, we should not expect to see interference. So when we send one photon and wait, and one photon and wait, we expect to see just two bright regions. But something crazy thing happened. They saw the interference pattern. There's a constructive interference and there's a destructive interference on the screen. So single particle somehow split into two and interfere each other. So this is not the only property of the photon. Electron also interfere, atom also interfere, molecule, even molecule with a 2,000 atom can interfere each other when they send it one by one. To explain this, we must conclude that each individual photon must travel both slits at the same time. Somehow one particle is in the two places and interfere itself and generate the interference pattern. So here you can see the constructive interference, and here you can see the destructive interference. And what's meant by constructive interference, you can see more particle in this place, and you can see less particle in that place. So what's meant by interfering? What wave is interfering? On the constructive place, you will find more particle, so higher probability to find the particle. For the destructive place, there's a less probability to find the particle. So it should be some kind of wave deciding the probability of the finding particle. So we call it probability wave. So since there are many locations, we can find the particle with the probability. This raises a crazy concept called superposition. So since particle can be upper place and lower path at the same time, and they should exist 50-50 probability, so that does not make sense intuitionally how the particle can be two places at the same time. So like normal people like me will be curious about where they are. I mean, even though mathematically there's two places at the same time, they must be one place. So people set up the detector and then try to check that does the particle go to upper slit or bottom slit. So it's a wave and probability, it does not matter, it just propagate, and we just stop it and measure. Did it go to upper slit? Okay, and let it go. And when you repeat this experiment, we found that interference pattern disappear. So when you look at it, it acts like a particle. And when we don't look at it, it suddenly become a wave. This is called decoherence. So whole universe depends on you watching it or not, and it raises a philosophical question. Does universe exist if you don't look at it? So Einstein said, I like to think that moon is there even I'm not looking at it. It's true. I mean, if we don't look at it, we hope that everything is there. And Schrödinger even doesn't like quantum mechanics, and also he doesn't like cat. So he put the cat in the box, and he also put the poison in the box. And this poison is a superposition state that 50% chance to become dangerous and 50% chance to be safe. And when you close the box, according to quantum mechanics, universe will split into two, one with the light cat and one with the dead cat. And when you open the box, you will decide the universe. It can be live, or we can decide and it can be dead. This denies the nature of the reality we live in. I mean, that's the nature of reality we believe in. And particle can be two places at the same time, and looking at it influence the universe. That doesn't sound right. But there's one more interesting phenomena because of wave behavior of the particle. So because of the wave property, photon can be two places at the same time, sure. But also, we cannot assign the deterministic position of the photon. So when you look at this wave, we don't really know where exactly it is. And when you stretch the wave, then I have more time to measure the frequency. So I know frequency better, but now I have no idea where the position is. And actually Einstein showed that frequency is related to momentum. So when we know more about the momentum, we don't know anything about the position. On the other hand, if I construct the wave, and if I make it concentrate the wave, then now I know the position exactly, but now I don't have enough time to measure the frequency. So then I have no idea what is my momentum is. So there's a relationship between uncertainty of the position and momentum. And Heisenberg discovered this uncertainty relationship, and he found some fundamental limit how much we can know. And this limit tells us that we cannot know simultaneously both position and momentum at the same time. And this uncertainty is not the practical limit of our measurement. Even though you spend billions of dollars making a better measurement, we cannot do it better. This is the fundamental limit of the universe. And this uncertainty principle about the frequency at the position is not something quantum. It's just a Fourier transformation. However, Heisenberg was able to connect this physical relationship of position and momentum uncertainty from the quantum mechanical effect. Because of this, Heisenberg and he got the Nobel Prize for creation of the quantum mechanics when he was 26. So the idea of the quantum object does not have a deterministic location, and we cannot assign the location with a certain probability. We can only assign the location with a certain probability, make a lot of physicists really uncomfortable. Especially Einstein was a strong prosecutor for quantum mechanics. he know a lot about quantum mechanics better than anyone at the time. But because his hard work, quantum mechanics can be here right now. I mean, because he first proposed about the photon level momentum, a lot of things in the quantum mechanics. But he does not want to accept this spooky reality. So he worked really hard to prove that quantum mechanics is incomplete. And he found a significant error on quantum mechanics, which is called entanglement. 1935, Einstein and his colleague designed a thought experiment to show that quantum mechanics is incomplete. Let's assume that we have two particles interact each other by collision or something like that. And according to the conservation of the total momentum, we know that two particles must share some information together. So for example, if one of the particles is going right direction and the other particle going to left direction, and they have the same mass, then we know that they should have the same velocity. And they also have to have a same identical position with the opposite sign. So if I measure the velocity, which is corresponding to the momentum, so if I measure one of the momentum of the particle, then I know right away that the other particle's momentum. By simply measuring the position of that particle, now I know the both information about the position and momentum. So when I measure one momentum, I know right away the other momentum without even measuring the other particle. I just need to simply measure the position to know both information at the same time, which violates the uncertainty principle, which violates the quantum mechanics. Only way to save the quantum mechanics is that when I measure one particle, it must send some information to other particle and tell them that I measured. So then other object can stop being a wave. However, this must happen instantaneously, no matter how far the two objects is separated. So I put the one particle in the Earth, put one particle in the Mars. When they interact each other, nothing changed them. They have to somehow share the information faster than the speed of the light instantaneously, which is crazy to believe that it's really happening. So Einstein called it spooky action in the distance. And it sounds like Einstein is correct because it's insane to believe that they can affect each other with that separation. For 30 years, people discuss about how can we experiment to test these two ideas. Bell found something that there's two different results will come out from these two interpretations. So if Einstein is correct, then there will be no such thing as sending information faster than the speed of the light. So the two particles will only have a classical correlation. And if the quantum mechanics is correct, then two particles will send information to other party. So then two particles will have more information than what Einstein predicted. And he worked out some math, and he found that we can measure two particles together to see the correlation. And Alan S. Beck proposed using the entangled photon, we can show that if Einstein is correct, the correlation should be less than 2. And if quantum mechanics is correct, the correlation should be more than 2. Here's a moment of truth. What is the nature of the reality? So it was all philosophical concept until 1982, Alan S. Beck conducted the experiment, and he prepared the two entangled photon and measured the correlation, and then result was 2.697, which is a lot larger than 2. This surprised a lot of people, and we now must accept this spooky reality from the quantum mechanics. Now, because of the experimental test, almost everybody except quantum mechanics is true. 100 years of people debating about what's reality, what's a quantum mechanics, a lot of philosophical questions. A lot of questions actually remain unsolved. But now we must move on to new area. Some people call it second revolution of the quantum mechanics. I would like to call keep calm and calculate. Famous physicist Sean Carroll compare our time with the smartphone. So like we are using the smartphone to do the banking and communication without really understanding how the transistor work. Physicists start using the quantum mechanics to predict extreme precision, utilize their experiment, enhance the technology, without trying to understand what it means about the nature of reality. This starts the second chapter of quantum mechanics. Now, we are in the new age that no one asks about, do you understand quantum mechanics? Now we focus on what can you do with the quantum mechanics. The new concepts, such as entanglement, superposition, interference, now can be used to improve technology or change the paradigm of current technology. For example, the concept of entanglement, which can send the information faster than light, now using the telecommunication and also create an extremely sensitive sensor. So this shows that the left side is the quantum teleportation actually using entangled photon satellite in China. So they are actually in the satellite, they using the entangled photon send the information and they can encrypt the information using the entangled photon. On the right side is using interference pattern. They can measure the gravitational wave from the faraway black hole. So this concept, entanglement, interference, and superposition, now we can use this one to also create the next generation computer called quantum computer. From here, my rest of the talk will be focused on the quantum computation. The beginning of the idea started with Richard Feynman in 1982. He found one of the problems that if we want to model the quantum system with our computer, it is showing the exponential slowdown. Because of the superposition and entanglement, make the problem really complicated. So I will give an example. Let's say there's some simple statistical toy model. We can generate binomial distribution. So the ball will drop from the input and decide to go to right or left with a 50% probability. And after decision, it will iterate the decision that going right or left, back and forth. And then it will reach to the basket. And when you look at this basket, we'll find this will follow the statistical distribution, binomial distribution. This can be simulated with the computer without too much problem. However, let's try with the quantum particle. The problem is that when the quantum particle decides right or left, it does not decide. It will go both together. So when it goes, it will go right and left together with a 50% probability. And at the second stage, it will go again, again, and again. It's even hard to make PowerPoint animation because now it just gets complicated. I cannot even make the animation. So this becomes really hard problem to solve in the classical computer because now it start superpositioning and interfere each other. So this becomes really difficult problem to solve. And actually, Scott Aronson and Alex Arkhipov showed that the problem is sharply hard complex class, which means it's a really hard problem to solve in the classical computer. And this makes exponential time. It needs exponential time to solve by the classical computer as you increase the size of the iteration. So how can you do it? The easiest way to solve the problem is actually just doing with the quantum particle. We just send the quantum particle to the double slit and triple slit and quadruple slit. We just repeat this experiment multiple times and measure what the result is. Then we can just get the result without using the computer. So we cannot simulate this problem with the classical computer, but we can experimentally just do it on the top of the table. So we can use the quantum system to simulate a difficult problem. So when Feynman suggested the quantum simulation in 1980, there was an undergraduate student in Caltech was inspired by his lecture, and he came up with one of the ideas that can compute the prime factorization, which is number theory problem. So prime factorization is a difficult problem to solve using the classical computer. Let's say you want to calculate how to factorize 21. This is easy. Computer can show that it's 7 times 3. But let's say we try to factor out a larger number, something like 32 quadrillion, 193 trillion, 216 billion, and 510 million, 801,043. Well, computer can, we just blow the computer. It's a hard problem to solve using the computer. Because of that, people apply this technique to secure our privacy in the internet. This is called RSA encryption. Let's say I send a message to my girlfriend, encrypt by the RSA 2048, and send it to my girlfriend. Theoretically, if somebody wants to read my message, using all the computer in the world to decode the message, it will take us 3,000 trillion years. So when somebody reads my message, me, my girlfriend, and you already died, and universe already died. Sad story. However, when you use the Schwarz algorithm, the problem is actually solvable. So if you have a perfect quantum computer, we should be able to solve in 8 hours, which is not that fast, but it's solvable. You can think about our security, such as banking and military, is all encrypted by the RSA 2048. This is very dangerous technology. Therefore, many governments start showing interest toward making a quantum computer due to the security concern. So basically, there are many quantum algorithms that can calculate the problem much faster than our computer. And a quantum computer is a platform for all the quantum simulation, quantum algorithm can be done. This is why there's many interest to building a quantum computer. And now from here, if you understand so far, you did a really great job. But I will go slightly deeper into the quantum computation, so I might lose some of the people from here. So there are many different ways to realize a quantum computation, such as a quantum circuit model, 1A quantum computation, and others. I will focus on the most widely used model, which is a quantum circuit model. Before I go to the circuit model, let's take a look at the classical circuit. Here, we have a 5-channel. So we have a 5 bit of information. And as you increase the wire, we increase 1 more bit of information. Let's prepare some input state. 10101. 1 means that I send the light. 0 means that I don't send the light. So now we put some logic gate into the circuit, such as NOT and OR gate. So this gate depends on my input signal, change the output signal. For example, if I put a NOT gate, if I send a 0, it will emit 1. If I put 1, it will emit 0. And I use this combination of these NOT gates. I can make addition, subtraction, multiplication, etc. So I only need to find this right combination of the gate to calculate using the classical computer. So let's say some simple example. Let's say I want to find the password of the bike lock. Of course, there's a better algorithm to find it, but let's say we just find the simplest classical computer example. So in order to find the password of the bike lock, we need to try all one by one. So check this one, check that, and say we try all the combination until we find a good lock, correct lock. Quantum algorithm is slightly different with the classical algorithm. Our bit of information is encoded using the superposition. And after that, we compute the system using the gate that can entangle and interfere this superposition state. So this is quite different, and I will start talking about, first I will talk about the superposition. The classical circuit use bit of information 0 or 1, light on or off. However, quantum mechanics allow to be 2 places at the same time, so we can do it better. Photon, let's look at the double slit experiment. So photon can pass through only upper path, which we represent 0 here. So I will say pointed up because it's upper path, and it's 0. I just encode that up as a 0 information. And when it goes to the bottom path, I will rotate that arrow to be pointing down, and I will encode the information about the 1. But quantum mechanics allow that we can go both paths at the same time, so then I can have superposition state, which is not 0, not 1, it's a 50% chance of 0, 50% chance of 1. So I will rotate my arrow to the right and say this is superposition state. But there's also 2 different superposition states. I can either make a constructive interference, and I can either make a destructive interference. So I will say plus and minus, and I will rotate 180 degrees to represent the destructive interference. So we can say that it shows, so compared to the classical circuit, we only use 0 or 1. Now we have a more degree of freedom due to the superposition. In order to understand how to entangle and interfere that play the role in the quantum circuit, I think it will be easier to show actual example. So then I will introduce some of the quantum algorithm. Let's say we have a switch, and if it's working switch, then depend on my input position, so 0 or 1, it will change the light bulb. It can be on or off. But if it's broken, whatever I turn it on or not, it will not respond to my signal. And there's two other cases that it will be always on, and it will not respond to my signal, even though I turn it on and off. And when you look at all the possible scenario, we have 4 different kinds of scenario. 2 broken case, then whatever my input is, it does not respond, and it's only give a 0 or 1. Or the working case, that it will respond to my input, so then it will be correlated output or anti-correlated output. So when I put 0, it will give a 1, or when I put 0, it will only give it 0. So here's the problem. Let's say we want to find what's inside of this box. There's 4 different types of switch can be inside, but we want to check sending a bit of information into the box, and we want to find out what switch is in the box. So let's say if it's working switch, and then working switch that is correlated output, when I put the 0 state as an input, it will not do anything, nothing to the second state. So can I tell that this is working switch by trial 1? No, because broken switch will give me same output. When I put 0, it will give me 0. So just by checking one time, I cannot really tell that this is working or broken. In order to tell this is working or broken, I need to prepare one more time with the opposite input state down and see that this flipped the second bit. So then I know that when it flip, then this is not broken switch, it is working switch. And this is a limitation of the classical computation, because we need to check all the possibility one by one. If we use the quantum computation, we can do it better. Let's say we prepare the state with the superposition state, which is either 0 or 1 at the same time. What happens when you put it into this superposition state into the circuit? Well, this is 0 and 1 at the same time, and my output will be depend on the 0 or 1. So when I put this circuit, actually the universe will split into 2 and give a flipping the bottom one or not flipping the bottom one. So then we have a 2 universe coexist at the same time. One universe have a up down, and the other universe have a down up. And this is entanglement, because when I measure the bottom qubit, it will decide which universe to collapse and then affect the other qubit to be change their state. What if we send both superposition state? We prepare like this and send it into the circuit. It will create something crazy. So let's say I put it into this circuit. It will split the universe into the 4, because of when it is up, it will not flip, but also we can have a 0 or 1 because they are superposition. And my input state can be 1, then it will all flip, but also they have a 2 possibility. So then we have a 4 different universe. And this universe will destructively interfere each other. When you do the math, you will find that this whole 4 scenario will start interfere and collapse to one universe, which is that the top qubit will be rotated. So we can check that when you send this superposition state into this broken circuit, nothing will happen because of the constructive interference. However, when you put this superposition state to the working circuit, this will flip the top qubit because of the destructive interference. So just by simply measuring the top qubit, we know that this is working or broken just with one trial. So this is the advantage of the quantum computation. If you cannot follow detail, here's a summary. So quantum algorithm, first rotate the state to be in the superposition state, and then when you compute the problem, universe will split into 2 and entangle each other and interfere each other constructively and destructively and converge to one solution. And this is introduced by Dutch, and this is known as Dutch algorithm. As I have shown you that 2 qubit, we can see twice faster than speed of the classical computer. If the problem size increased, the normal computer will exponentially increase to the n to solve the problem. However, quantum computer only suffer the linear time to solve the problem. So we can say that certain problem quantum computer can solve exponentially faster than classical computer. And he's the first person who discovered this quantum algorithm and first person to show that we have an exponential advantage. Now we have many algorithms. IBM have a lot of library of the circuit, have optimized the stock market, machine learning algorithm online. Since I'm an advocate for the IBM Qiskit, I want to advertise some of the feature. You can use the IBM quantum computer anywhere in the world. Let's say you want to program the molecular behavior, or make a vaccine, or optimize the portfolio for the stock market. Then you will use your laptop and your programming code like Python to program what you want to do. Qiskit have there is already a lot of library of the circuit, so you can use that to program it and send it to IBM quantum computer. Then it will calculate actual quantum circuit and give it back to you the result. So what can you do with the answer if you have a perfect quantum computer? If you have a perfect quantum computer, just with a 50 qubit, we can simulate whole human information. More than 200 qubit, we can simulate the entire observable universe. Think about it. Just with the 200 photon or atom, you can put it on your hand. It's even smaller, so then you can even see on your naked eye. It has exponential power to solve the problem. Currently, we do not have a perfect quantum computer because of the decoherence. As I mentioned, when you look at it, it becomes a particle. When we don't look at it, it becomes a wave. So if I say a little bit more accurately, which is that if we have any ability to extract the information out from the system, then even though we don't look at it, it can influence the state. So any vibration, any heat, any sound coming out from the quantum computer can influence the quantum computation. So because of that, if we can know the information, this will create the error on the quantum computer. So for this reason, we cannot isolate the quantum computer perfectly isolate from the environment. So that's why we try our best. I mean, IBM tried best to put their quantum computer inside of the fridge. So then it's cold, nothing will coming out. But because of the error, even though you make it really, really good, 50 to 100 qubit cannot do the work, cannot simulate the universe. So we have to increase the number of the qubit, but also have to reduce the noise of the quantum computer. Yet, we don't have a perfect quantum computer, but we are in the most exciting time in human history. This is something beyond any revolution human ever experienced. We are reducing the error and increasing number of the qubit exponentially. And this increased the power of the quantum computation exponentially. So just take a look how the computer revolutionized our society. We send the person to the moon, design the new drug, and predicting the weather. And if we keep growing our power of the quantum computer as rate is now, building quantum computer is just a matter of the time. And we might cure the disease, complete prediction of the weather, even control the weather, optimize, simulate the battery and solar panel so then we can solve the energy problem. I really hope, maybe, that we might answer some philosophical question of our life. Thank you for your time and attention.